Welcome to Mathematical Analysis. Today, we are going to explore a powerful tool called Cauchy's nth root test. If you have ever wondered how we can add up an infinite number of items and still get a finite, manageable result, you are in the right place. We will build this understanding completely from the ground up, step by step. Let us start by imagining you are building a tower by stacking blocks, where each new block is smaller than the last. In mathematics, adding an infinite sequence of numbers is called an infinite series. We want to know if the total sum reaches a maximum finite number, which we call convergence, or if it blows up to infinity, which is divergence. Cauchy's nth root test acts like a strict inspector to measure exactly how fast our blocks are shrinking, ensuring the tower does not topple. Now that we understand what we are looking for, let us see how the inspector works. The test looks at the nth block in our series and takes its nth root. This extracts the base growth or shrinkage rate of the sequence. If this shrinkage factor is strictly less than 1, it tells us the pieces are getting tiny so quickly that their total sum is perfectly manageable. It is a brilliant way to simplify complex sequences into a single, understandable rate of change. This brings us to the mathematical heart of the test. We calculate a special limit called L. We take the limit as n approaches infinity of the nth root of the nth term. The symbol a sub n represents the formula for the numbers we are adding. Taking the nth root or raising to the power of 1 over n strips away any nth power present in the term. If the resulting limit L is less than 1, the series converges. If L is greater than 1, it diverges. If L equals exactly 1, the test is inconclusive and we must try something else. Before we move on to why this works, let us see this formula in action with a concrete example. We are asked to determine if a specific infinite series converges. The series has the term 1/2 plus 1 over n, all raised to the power of n. Because the entire expression is raised to the power of n, Cauchy's nth root test is the perfect strategy. We start by clearly identifying our nth term, a sub n, so we know exactly what to plug into our limit formula. Continuing with our setup, we apply the root test by taking the limit as n goes to infinity of the nth root of our term. We place the entire expression inside square brackets and raise it to the power of 1 over n. Because raising a power to another power means we multiply the exponents, the n and the 1 over n perfectly cancel each other out. This beautifully simplifies our limit, stripping away the outer exponent entirely, leaving us with a much easier expression to evaluate. Now we evaluate the simplified limit. As n grows infinitely large, the fraction 1 over n shrinks down to exactly 0. The constant 1/2 remains completely unaffected by the changing n. Adding these together, our final limit L is exactly 1/2. Since 1/2 is strictly less than 1, the test conclusively tells us that the series converges. Physically, the pieces shrink so rapidly that their accumulated sum safely settles at a finite number, rather than growing out of control. Now that we have seen a converging series, let us look at a scenario where a series blows up to infinity. We have a new series where the term is 2 minus 1 over n, all raised to the power of n. Just like before, the global nth power is a flashing neon sign telling us to use the root test. We set up the limit by raising our nth term to the power of 1 over n, which neutralizes the outer exponent and reveals the true behavior of the base. Let us finish evaluating this second example. The exponents cancel out, leaving us with the limit of 2 minus 1 over n. As n approaches infinity, 1 over n becomes 0. Subtracting 0 from 2 leaves us with a final limit of 2. Because 2 is strictly greater than 1, the series is strictly divergent. This means the terms are not shrinking fast enough. Their base growth rate is essentially doubling, so the total sum will violently explode toward infinity. So, we have successfully used the formula to test two series. This brings us to an important question. Why does comparing this limit to the number 1 work? The secret lies in comparing a complicated series to a much simpler, well-understood geometric series. We start with our basic assumption that the limit of the nth root of our terms equals some number L. By the formal definition of a limit, for very large values of n, we can approximate the nth root of our term as being roughly equal to L. This approximation is the crucial first step in our logical derivation. Continuing our derivation, we want to isolate the original term to see how it behaves. We raise both sides of our approximation to the power of n. This reveals something beautiful. For very large values of n, our complicated term is essentially just the number L raised to the power of n. This is exactly the format of a geometric series. Because we assumed L is a number less than 1, we have a geometric series with a multiplier smaller than 1, which always converges. Therefore, our original series must also converge, proving why the number 1 is the critical boundary. To make this proof completely clear, let us look at it visually. The diagram shows a graph with the index n on the horizontal axis and the term value on the vertical axis. The smooth dashed line represents the perfectly predictable geometric series L to the power of n, which shrinks down to 0. The solid line with dots represents our actual series terms. The root test guarantees that eventually our sequence gets trapped underneath the converging geometric series, forcing it to converge as well. Now that we understand the core mechanism, we must address a crucial detail. What happens if the limit of the nth root does not actually exist because the sequence bounces back and forth? In these cases, Cauchy's nth root test uses a more powerful form called the limit superior. This looks at the worst case scenario, or the highest peaks the sequence hits as it goes to infinity. As long as these highest bounces eventually stay strictly below 1, the total sum will still be finite. As you continue your studies, you will frequently use D'Alembert's ratio test. It is vital to understand how it compares to the root test. The mathematical truth is that the root test is always at least as powerful as the ratio test. If the ratio test works, the root test will also work and give the exact same answer. However, there are many fluctuating series where the ratio test fails completely, yet the root test easily proves convergence. It is the stronger, more reliable older sibling. Before we conclude, let us understand why this matters outside the classroom. Understanding whether an infinite series converges or diverges is the foundation of how computers calculate complex functions. When a calculator computes a sine or exponential function, it adds up an infinite Taylor series. If that series diverges, the calculator would crash or return an error. Engineers in quantum mechanics and signal processing also rely on these tests to ensure that the energy of a physical system remains finite and stable in the real world. We have covered a lot of ground today. Let us review the key takeaways. Cauchy's nth root test extracts the underlying growth or decay rate of a sequence by taking the limit of the nth root of the nth term. If this rate is strictly less than 1, the series safely converges. If it is greater than 1, it diverges. You now have a robust, powerful tool for analyzing infinite series, especially those wrapped in nth powers. Great job following along.